All right, so let's talk about parallel compilation in Scala. This is a pretty hot topic, right? Because we all want our Scala compiler to be faster. So that's one of the ways to approach the problem. Let's see. So here at Twitter, we developed a whole new experimental compiler to explore avenues in that direction. Let's see what kind of numbers we arrived at. Some of you may have already saw the spoiler. That was very careless of me. But anyway, a few words about myself. From 2011 to 2016, I was a PhD student in Martin Odersky's lab in Lausanne, Switzerland. And shortly after graduating from getting my PhD from Martin, I joined Twitter. So currently I serve as a tech lead of the Advanced Scala Tools team here. And you know, speaking of my work in the community, you may have heard of Scala macros. That was my PhD thesis. There's the Scala meta thing, the meta programming library for next generation tooling. I gave a few talks about it before, but not today. And RSC, that's a new hotness. So a year ago, we announced that we'll be developing a completely new compiler from scratch to see how far we can get in speeding up Scala. And today, at the same conference, just a year later, we're really happy to show some initial results. All right, so concretely, in the talk today, I will give a brief recap of the thing that we presented last year, for those of you guys who are not completely sure what RSC is. Then we will discuss the avenues that we explored how to make our prototype, last year's prototype, useful. Because it was fun, but it wasn't immediately useful for anything. That was quite a challenge, and we'd like to share this experience with others so that they can benefit from it. Then we will talk about the key insight that one of our team members had, how to use RSC, how to use our compiler tag to speed things up in real projects, like in SBT, for instance. And finally, I'll demonstrate the experimental results. Okay, so the quick recap. RSC is, that's the tagline from GitHub. It's an experimental Scala compiler focused on compilation speed. So the experimental thing, it means that we can just, at some point throw it away and call it a day, and it'll be great, right? As long as we learn from our experiments. Well, what Scala and what compiler means, I guess that's pretty clear. And focused on compilation speed, this basically says that we are not interested in anything else, so just compilation speed. And this very, very narrow focus, it allows us to do super targeted experiments. So perhaps the results of those experiments would not be immediately useful for the Scala compiler or for Dadi, but at least we'll know the boundaries where we can go. So concretely, our research goal, that would be the success criteria. If, say, in a few years, a Scala compilation for typical code bases, for whatever definition of typical, right? If it's 5 to 10 times faster, then we're golden. And I believe we're on track to achieving that goal. But as usual, since these are experiments, it's research, everything can fail. Although today we will see evidence of moving towards that number. All right. So when we started RSC, I already mentioned that it was designed from scratch. We figured out 3 axioms. So first of all, we decided to rewrite it completely. So last year I talked about this a little bit more, but existing Scala compilers, they're pretty big. So 80K lines of code, 140K lines of code. So clearly, if you were to do fundamental experiments in such a compiler, say completely remove existing ASTs and replace them with something else, that would be very hard. In comparison, our compiler is about 20K lines of code. So it's feasible to just throw away everything completely and rewrite it in a month. And well, that's what experimentation is about. Then last year, we decided to start small. That is, to pick a very small subset of Scala and just implement it, see how fast we can get. So clearly, the result would be not useful for practical use, but it would show the limits of Scala compilation speed. And finally, so this was a bit controversial at the time of our announcement, we do not intend to fork the language. Instead, our goal is to contribute to the community through our experiments. So ideally, if Scala-C or the Dotty compiler, the new Scala compiler, if they become much, much faster because they use some of our ideas, that's awesome and that's great. This is what open source is about, and we're very happy to give back to the community. Let's take a super quick example of how RSC works, and this will familiarize us with the terminology that we'll need further. So here we have a hello world program with some random classes, some methods, but the bottom line is that on the left-hand side we have one source file, on the right-hand side we have another source file, and clearly they use other definitions like X or C, which are not shown here. So what happens next? What happens when RSC sees those source files? It will parse them into something called abstract syntax trees, some representation for the program, and then it will do something called schedule. So basically, it will go through all definitions that are visible from other files, and it will mark them somehow. It will remember them in a list or a hash map, whatever. So what's critical here is that these definitions, we call them outlines. This is the only thing that is necessary to figure out dependencies between source files. So for instance, val b that is shown on the left, it's completely irrelevant to other files in the project because no one can reference that val b, right? But method foo in class A is definitely relevant, and type checking other files in the project may need the type signature of that method. So we make a note of all those definitions, and then we do something called scope. That's another phase in the RSC compiler. So we resolve the imports, and we resolve extends clauses. So basically, at this point, we know exactly what kind of names are visible everywhere in the program. And the next step, and now things are colored in red, it's pretty special. So thanks to the preparatory work that we did before in the previous two phases, we can do everything else in parallel. So just because we know all the names that are available at any point in the program, we can resolve those names completely in parallel. So those foo, C, A, and B, that's pretty neat. But that's not the main cool thing. The really cool thing, it happens here. So again, red parts, they signify parallel processing. So after those names have been resolved, and after we know all the type signatures of publicly visible members in the program, so those type signatures, I will be calling them outlines from now on. So once we know the outlines, everything else can be done in parallel. So we can create, if we're really adventurous, we can create a thread per method body, and just, with this fictional hardware that has tens of thousands of threads, we theoretically can do things very quickly. So that's the kind of experiments that we were running a year ago, and the results were quite promising. So we hacked up a prototype type checker for a small subset of Scala. So this thing, it wasn't meant for real use. That's why we only supported source dependencies. So we could not link to jars, for instance. Everything had to be defined in sources. And finally, it wasn't quite a type checker because it only could do name resolution. So it did not do type inference, implicit search, nothing like that. So we were interested in obtaining a hard upper bound of how fast things could be. And well, here are the numbers. So we took an implementation of regular expressions ported from Java, so it was super simple Scala code. It was super simple, but not trivial. So it still contained method calls, class definitions, type applications. And what we figured out in this case study is that our prototype type checker, which was very limited, as discussed on the previous slide, it was 25 times faster than the full Scala-C type checker. So that's quite promising, I think. However, this brings up another question. So we can resolve names super quickly. We cannot do type inference. We cannot do anything else. We cannot emit bytecode. So what now? It was fun. So what happens? Do we now close the project and move on, right? That was a really tough point in the life cycle of RSC because we just did a very impressive demo and we did not know where exactly to go from there. And so in this part of the presentation, I'd like to share some of the ideas that we explored. First of all, here's the obvious one. How about we just implement the entire compiler So in addition to this type checker for the small subset of the language, how about we create a full Scala compiler for a small subset of Scala? And since we resolved all the names, we're already very, very close to Emit in bytecode. So let's just resolve the names and then somehow write a backend. So backend is a thing that takes those names and emits class files. Perhaps we could make this happen. However, there were some reasons not to do that. So first of all, the first reason was that if we were to write all of this on our own, the scope of the project would blow up significantly. Before I told you guys how cool it is to have a small compiler, like 5K lines of code, 20K lines of code. But if you have to do everything, it becomes unwieldy very, very quickly. So our only other hope was to integrate with backends in other compilers, like the Scala compiler or Dari. But unfortunately, at this point, both backends, they're tied to compiler internals of individual compilers. There is a proposal that Adrian from Lightband submitted to the Scala Center recently to have Tasty as a unified intermediate format that works across Scala C and Dari. And in that case, if we have that standard, then we can have one single backend that works for everyone, RSC included. So that sounds very promising, but that was definitely not even in the cards a year ago. So long story short, we discarded this idea. What happened next is we thought about producing SemanticDB instead of class files. So SemanticDB is, to put it in a nutshell, is a data schema for semantic information about Scala and Java programs. So here you can see a protobuf definition of a central data structure in the schema. So basically, we can emit various symbol informations, compiler diagnostics, compiler synthetics, whatever for source files that you have. And then based on that information, we have a bunch of tools that can leverage those payloads. So MetaBrowse, it's a static code browser, generates static websites. Metals is Scala Meta LS language server. It's kind of like an IDE, and so on and so forth. So clearly, what we could do with RSC, with our ability to resolve names very quickly, we could have a killer feature. We could have a killer tool that's so fast that it's just unbelievable, and it makes things much, much better. So of those tools, I will not go into details, but a super fast IDE, it would actually be nice. So IntelliJ indexing, sometimes it's quite annoying, especially on big projects. So what if we could do that super, super quickly? That's definitely within reach. However, an IDE, a full-fledged IDE, it's more than just indexing or type check. And that's, again, a scope blow-up. So we thought about this and decided that it's not super practically feasible, at least not in the near future. And then there was another idea. So at one point, we had an improvised meeting with one of my colleagues, Stu Hood, who works here at Twitter as well. So he dragged me into the meeting room and explained what I'm going to explain to you guys. So he said, so hey, Eugene, you already computed outlines, but how about you save them to disk in the format the Scala compiler understands? And then after all the stuff is saved to disk, you can launch multiple Scala compilers. Not RSC compilers, but Scala compilers. And this way you could compile things in parallel, supposedly making things faster. And so that was a real breakthrough. So finally, we saw something that can be implemented within a few quarters as opposed to a few years. And the rest of the talk is going to be about just that. So enter multi-phase compilation. Let's take a fictional example of a four-project configuration. So you have projects A, B, C, and D. A is at the root. It does not depend on anything. Then B depends on A, C depends on A, and D depends on C. It sounds very confusing, but I hope that this chart, this Gantt chart, it'll help you out. So this is how normal compilation would work. This is how a Scala build tool would work without pointing fingers or anything. So that's first you compile A completely from beginning to the end, and then you start dependent compilations, B and C. And finally, once C is compiled, you compile D, and here you go. So that's how build tools basically work at this point. And you can notice that there is already, depending on the configuration dependencies between projects, there is already some degree of parallelism in those builds. So thanks to outlines, we can do this a bit faster. So let's say we have outline and we have implemented outline and via RSC or other means. And outlining takes just 50% of compilation time. Because we don't emit bytecode, we just compute public type signatures, nothing else. And so in that case, to start compiling projects B and C, you just need an outline of A. You don't need to wait all the way up to completion of Scala CA. And as you can see, this already brings significant speedups. So we were at 4.5 seconds, now we're at 3 seconds. Obviously, this is a fictional example. This is all theorizing. So in practice, it's a bit different, but you see the idea. So that's pretty good, but we can do even better. So remember, RSC was very fast at resolving names. So actually, for RSC, the picture looks like this. My outlining is so fast. And again, now we're more than 2 times faster. But that's not the end. We can do even more. So how about we take those big red bars, and how about we split them up like this? So in this example, we took each project, and we split that project into 2 parts. And then we compile those parts independently of each other, so we literally create independent compilers for all of them. And clearly, this raises the questions, so what if first part depends on the second part? What do you do with this? And the critical insight here that once you compute outlines for A, for the entire project A, that's all that's necessary to resolve those dependencies. So if A1 depends on A2, then this is taken care of by this small blue outline A thing. And what's pretty cool about this, we're more than 3 times faster than the original number, just because of splitting things up and because there is this outlining tool that's available. And because we can dump outlines in the format that the Scala compiler understands. Well, clearly you need to have impressive hardware to take care of this. So here we have 8 or even more than 8 threads, depending on the time. But if you have that hardware, you can be very fast. So another fun experiment that we did, it didn't quite pan out, but I wanted to mention it. So how about we put all those targets together, all those projects together, ignore any boundaries between them, and then we outline everything all together at once, and then we slice and dice that unified project, this super project, super target, into 8 parts. So ideally, what that would lead to is uniform usage of all cores that are available on your computer, disregarding all the dependencies between different projects. But why this did not work out well in our case is that, see now there's a big blue line which is blocking everything. So we do not support parallel outlining at this point, which means that this super target parallelism thing, it doesn't work out quite well. So perhaps it will in the future, but not at the moment. A little bit of practicalities. Again, I'd like to just share the experience that we obtained while working on the project. So first of all, with this approach, we don't need to limit ourselves to a small subset of Scala. Because in order to type check type signatures, actually, you don't need to support too many features, right? So there's type applications, type projections, blah, 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 but it's not too much. And whatever's happening in method bodies, you don't care about this at all. If you do this one weird trick, right? You require that return types for all defs and vals are explicitly annotated. So in case when you don't rely on type inference in public signatures, you completely disregard method bodies. So that's arguably one could say that this is already a best practice to do this. But this is still a significant change to the developer workflow. Luckily, we have a tool called ScalaFix, which was developed in SemanticDB. Perhaps you guys saw that in one of the previous slides, that can take care of that automatically. So at least that's taken care of. There are some complications regarding Java support, but I'm running out of time, so I'll just skip that part. So anyway, let's get into experimental results, the numbers that I promised before. Well, first of all, a little bit about the hardware. The only thing that's of note here for these benchmarks is that we used a pretty powerful CPU. It's actually a 2 CPU configuration, 16 cores each. Well, whatever memory, whatever SSD, as long as memory is enough and it's SSD, not HDD, and it's not holding us back. Then we took, here's the software configuration. So we use Scala 2.11 for our experiments. We use JDK 1.8. We use whatever build of RSC, and there's something called warp that I'll mention in just a few words. So warp is a toy build tool that we hacked up just specifically for this demo. How cool is that, right? So we were to give a talk, and then we just wrote a simple build tool. I wouldn't call it simple. I would call it JBT. It's like joke build tool. It doesn't even do fingerprinting. It doesn't do incremental compilation. All it does, it just calls RSC and ScalaC in the right order. So this thing, again, it shows upper bound of performance that we can achieve. Now, speaking of the case study, so we took a real-world project, which uses actually a lot of advanced Scala features. So there's something called Twitter util. It's a collection of utilities that we use in our mono repo internally, and they're also available in the open. It contains 60 of what we call targets, which is basically small projects, right? So here at Twitter, we use a build tool called pans, and this is how projects are called there. And it's possible to have lots of those projects, targets, and which is why 75K lines of code Twitter util, it has 60 projects. So here's that. And now, what exactly did we benchmark? So we benchmarked one-phase compilation with a hot JVM on different powers of 2 threads. And we benchmarked three-phase compilation, which is basically compute outlines, compile Scala targets, and then compile Java targets. Some things that we noticed that hyper-threading did not work well in those benchmarks. So we didn't even try with 64 threads, not on the graphs anyway. It just makes things worse somehow. And then, speaking of splitting targets into parts, we split targets into batches of 5 files. So the number of parts is dynamic, actually. And now, finally, can we get to the numbers? Jesus Christ, it's 20 minutes already. Where are the numbers? So here they are. First of all, one-phase compilation. This is what your regular build tool can do. So with the build configuration like we have in Twitter util, things actually can scale up to 4 threads. So see, with 1 thread it starts at 37 seconds, and then at 4 threads it's at 18 seconds, and then pretty much flattens out. So that's 2.25x speed up on 32 threads. And here's what we can do thanks to RSC, and thanks to this outlining compilation strategy. We start way, way up. It didn't even fit into the slide, right? Because there's lots of work. So remember, there were lots of red and blue bars on the picture. So this is where the extra work comes from. And then, as you can see, it scales well up until 16 threads, which is so much better than the blue thing. And ultimately, it settles down at a little bit above 6 seconds, which is 2.7 times faster than what you can achieve with your regular build tool. So some comments about that. We don't have much time to discuss the results here, why it ended up being like this. But ultimately, thanks to outlining, I believe we're able to extract more parallelism, even from unfavorable dependency configurations in your builds than usually. So you saw it was just 75K lines of code. It's not a big project by any measure. But still, we obtained 2.7x speedups. So hopefully, for really big projects, and we have plenty of them here at Twitter, it will be much bigger. But clearly, you need powerful hardware to make use of that. Now we're almost at the summary. So I'll quickly go through related work. The slides will be posted shortly on my Twitter. But basically, there is related work. So this whole outlining thing, it started from a project called Kentucky Mule, which was done by my former colleague from PFL, Grzegorz Kosakowski. And then, we took that idea and we ran with it in RSC. But there's also other work done concurrently. So there is a build tool, or not a build tool, anyway, called Bloop that's developed at Scala Center. They experimented with something similar, although they don't have this fast outlining as we do. And there is also related work going on in Dadi, the new Scala compiler. So speaking of credits, lots of credit goes to Martin Odersky because writing a Scala compiler from scratch, this is a terrifying endeavor, and just knowing that Martin did that twice, it was a big help. So then I would also like to thank my former colleague from PFL, Denis Shabalin, who developed Scala Native. So he demonstrated that Scala programs can be very, very fast. So thanks to Scala Native, you can have CLI tools that start in milliseconds as opposed to seconds. So Greg, we already mentioned him for outlining. And then, guys, my colleagues from Twitter, we have the Advanced Scala Tools team who worked on RSC. We have Stu, who came up with this idea of two-phase compilation. And our build team, they're working on integration between RSC and PANS, the build tool that we're using at Twitter. OK, so to sum it up, we can outline things very, very quickly, both for Scala and Java. And apparently, that's useful if you have powerful hardware. Thank you.